Okay, so we'll get started on chapter 6, and next class, if you have questions about the exam, still after taking it home and working on it, we can do that. I don't want to do it now because you're gonna take the exams home to work on, right? So, yes, ma'am. No. Whichever ones you want to get half the credit you missed for, do it. If you just want to do one, it's up to you. It's your call. You will get credit for half of the points you missed in that specific question. If it's Otherwise, you'll get the same grade that you had before, right? Okay, so frequency response, body plots, and resonance. So, have you been exposed to something like this in chemical engineering or not? Not yet? Okay, so I'm sure you will take a controls course in chemical engineering, right? Any physical system will have a frequency response. So what we mean by frequency response is the response or the response from input to output of the system depending on how fast or the content of the input, the frequency content of the input. So for example, if you have a car, both cars have the same steady state solution, right? Both cars you can go to 100 kilometers per hour, a Corolla and a Lamborghini, right? They can both go to 100 kilometers per hour. So the steady state solution is the same. They will both meet the 100 kilometers per hour requirement. But the transient response of the system will differ, right? So a Lamborghini, you press the acceleration, it will go from 0 to 100 in a certain amount of time. The Toyota will go from 0 to 100 in a certain amount of time, right? So this amount of time and how the system responds to the input stimulus is what is called frequency response. It's called transfer function, and we represent the transfer function as a frequency response, and I will show how. So if I have a Lamborghini, it will have a certain frequency, a certain transfer function, right? So its ability to accelerate from 0 to 100 will be a certain ability, right? Based on the design of the vehicle itself, right? But I can press the accelerator pad very quickly, or I can press the accelerator pad slowly, right? So that is where the frequency components of the input will affect the output, right? But how the system takes this input and processes it will not change. This is the system. And the system will respond to different input stimuli in a different way depending on the spectral content of this stimulus. If the pad is pushed very fast or the pad is pushed very slowly, the car will respond based on the design of the car. The design of the car does not change. The design of the car is called the transfer function of the car. The chemical process is the same thing. Your chemical plant has a certain transfer function, right? So then you buy a big pump and you push flow very quickly, versus you buy a flow pump and you reduce the flow rate, right? So your plant design has not changed. Your plant will have a certain transfer function, and this transfer function will take this input and process it and give you a certain output. If this input is at a high flow rate versus this input at a low flow rate, your plant will respond in a certain way based on the design of the plant, right? So the plant will have a transfer function, and the input will have certain flow rates or certain frequency components, either fast or slow, or high magnitudes or low magnitudes, right? So that's sort of the idea of a transfer function and frequency response. So the idea of a frequency response is, okay, you have an electrical circuit now. It's an electrical circuit. You will excite it at a certain frequency, right? If you excite it at a certain frequency, the output voltage on one capacitor, for example, will be a certain value. How about if you change the frequency? If you change the frequency of that signal, remember that in the last chapter we were looking at, the value of the impedances of L's and C's in a circuit. So the impedance of the inductance was equal to what? J omega L, right? So it had the frequency had an effect there. The impedance of a capacitor was 1 over J omega C. So there is an effect of the frequency there as well, right? So if you put in a voltage now that is at a different frequency, the current is equal to what? Voltage over the impedance. So It's the voltage at that frequency over the impedance at that specific frequency. That will produce a current. How about if I change the frequency? What happens? The voltage frequency will change. The value of the impedance will change. Hence, the current will also change. So if you take all of these different values of current at the different frequencies for the same circuit, okay, then that's what's called the frequency response. Right? So it's the same circuit. The circuit has a certain transfer function. By putting input stimuli or stimuluses at different frequencies and plotting the output, you're plotting the frequency response. And you can plot this frequency response on a linear scale, or you can plot this frequency response on a logarithmic scale. When you plot it on a logarithmic scale, we call that a body plot. Right? Why do we plot it on a logarithmic scale? Because sometimes it's easier to see things on a logarithmic scale. So if I would like to see what happens to the output voltage at 60 Hertz, right? When you plot output voltage magnitude versus frequency on a linear scale, it will look something like, for example, on a linear scale, for example, the output voltage versus frequency may look something like this, versus on a logarithmic scale for frequency. I'm talking about the logarithmic scale for frequency. So if I change this from linear scale to logarithmic scale, then I will get something that looks like this, for example, right? So at a certain frequency, 60 Hertz, at a certain frequency, 60 Hertz. These are the same values. This is in, sorry, this is voltage, and this is voltage, but this is plotted versus a logarithmic scale, and this is plotted versus a linear scale, and this is plotted versus a logarithmic scale. What the logarithmic scale does is amplify and compress values depending on the differences between the numbers. And we will plot certain waveforms and see what they look like. But if I want to, for example, this is a circuit. I have a box here that has a certain circuit inside, and I'm supplying this circuit with a certain voltage source, and I'm looking at the two terminals that I have here, right? And I measure, this is my input voltage, and this is my output voltage. I'm measuring the output voltage, and I get these numbers. While changing the frequency of the input, right? While changing the frequency of the input, I will get a certain value of the output, right? And I plot the numbers. I can take that and plot it on a logarithmic scale, same numbers, plotted on a logarithmic scale will just have different, the spacing and the values will have different, the spacing and values will be different. And we will see how to convert from linear scale to logarithmic scale. But the idea is this system, or these numbers and these numbers are the same physical system. But we just represented the numbers differently on a linear scale versus a logarithmic scale to amplify or compress certain things so that we can understand the phenomena better. Okay? We will see what that, and this is what's called the body plot. And resonance is a property in any physical system where an input stimulus can change the output significantly at a certain frequency. Okay, so for example, an electrical circuit can be, you can have an electrical circuit that can have an R, L, and a C, right? This has an impedance R, this has an impedance J omega L, this has an impedance 1 over J omega C, right? If I put a voltage source here, and I look at the current, right? What is the current that's flowing in this circuit? I is equal to what? V over What is the total impedance? Sum. So it's R plus J omega L minus J over J times 1 over omega C. Right? I brought the J up here. Right? So, or I can rewrite this as V over R plus J omega L minus 1 over omega C. Right? This L is a certain value. Right? This C is a certain value. Right? At a certain frequency, right, I can make this bracket go to 0. Correct? For a certain value of omega, I have a certain value of L, a certain value of C. This bracket here, everything, the omega L minus 1 over omega C, will only be 0 for a certain value of omega, not all values of omega. Right? So if I change the value of omega, it will depend on the value of L and C, whether this parenthesis, the value of parenthesis is 0 or not. Right? So there is a condition where this circuit will have resonance. Meaning, in this case, if the R is very small and the current in general at 60 Hertz is a small value. What does this mean? It means that omega L and 1 over J omega C have a significant value at 60 Hertz. Right? But I change this frequency to 20 kilohertz. If I change this frequency to 20 kilohertz, this goes away. What's going to happen to the current? I said R is small. So what will happen to the current? It will be very large because I said R is very small and the voltage magnitude is the same, but the frequency just changed. So V over R will be a very large number in this case because I said R is small, and this everything in parentheses disappears. So the resonant frequency for this circuit, in this case, was 20 kilohertz. If that's what caused this bracket to disappear, right? So electrical circuits, mechanical systems, fluid systems, everything will have a frequency response, and everything will have a resonant frequency. All physical systems will have a resonant frequency, like bridges. Have you ever seen these YouTube videos where a bridge, because of the wind, starts shaking, and then collapsing? So it's because of the resonant frequency of the bridge. So the wind was blowing against the bridge at a certain speed. This speed made the bridge sway at a certain frequency. If this happens to be the resonant frequency of the bridge will, instead of swaying slowly and being a damped system, it will lose this sort of something effect like the omega L and omega C effect, and the vibration will increase, or the swaying magnitude will increase, and it will just break. Mechanical systems, same thing. Motors with shafts that rotate, they have a resonant frequency. A shaft will rotate at a certain speed. You never want to rotate the shaft at its resonant frequency, because if you rotate the shaft at its resonant frequency, it will vibrate. You will not be able to control it anymore. If you move a motor, that's why when you design a generator or a motor or any rotating piece of equipment, you want to make its running speed far away from the resonant frequency of the system. Okay? Because otherwise, if you make its resonant frequency the same as its rated running speed, then you put a small stimulus, supply a small amount of electrical power, and it will spin like crazy, right? Uncontrollably. So everything will have a resonance frequency. I'm not very familiar with fluid system, resonance frequencies in fluid systems, honestly. Maybe this is something somebody can look at and teach us next time, right? So I gave you a mechanical analogy and I gave you electrical analogy. It'd be interesting if somebody or a civil analogy. If somebody can come up with a chemical analogy for resonance, maybe we can discuss it next time. Bonus point. Okay, would that help? 0.5% bonus for somebody that comes up with a good discussion about resonance in chemical or fluid systems. Okay, so that's what this chapter is about, right? So that's what you're going to do. Of course, we're going to talk about it more from the electrical circuit perspective. Okay, so from an electrical circuit perspective, you're you have a circuit and you're putting in voltages and currents into the circuit, and you're looking at certain output signals. So you're looking at voltage at the output of across the capacitor, voltage across the inductor, current to the inductor. You're looking at some physical phenomena related to the circuit. You're looking at, for example, you have a temperature sensor that is basically a resistance. Temperature sensors are, RTD, resistive temperature sensors. They're basically a resistor. So sometimes you're measuring the voltage across the resistor, and you're measuring, and that resistor, for example, you would put next to your system that is heating up, right? So you want to make sure that the output of the measurement circuit is a true replica of the temperature that you're measuring, right? But you have this resistor on there, and this resistor is going to go to a different circuit to do what? I mean, the resistor by itself doesn't do anything, right? For you to measure temperature using a resistive temperature device, you have this device on top of the equipment you want to measure temperature for. And the resistor by itself can do nothing. You have to put voltage across it, and then current will flow. When current flows, and you measure the voltage across the resistor in that case, and the resistance change will cause the voltage across the resistance to change, right? So you have to pump in a certain fixed value of current into the resistor and measure the corresponding output voltage. The resistance will change depending on the value of temperature, and you're going to take that. But this change, how fast is it happening? Is it happening at the same rate as the equipment is being heated, or does this resistance have some time constant to heat up? Right? May or may not. It's a mass. A mass will have, will have a thermal capacity, right? So you would need to make sure that this thermal capacity will give you enough, will not delay the change in temperature, the measured temperature, so that you know what the real temperature is of your physical system. So even a small resistor that's used as a temperature sensor will have its own transfer function, right? So it's okay, and I discussed the idea of each frequency component of the input, right? So I gave the example of a car where you have a accelerator pedal, and you can either push the pedal down very quickly, or you push the pedal down very slowly. One is a low frequency response. You will get the low frequency response of the car if you push the pedal down very, very slowly. One is a you will get the high frequency response of the car. The car will accelerate very quickly in a short period of time, in that case, right? In the electrical signal, you can combine. You can have signals of different frequencies put into the circuit, right? I can have two different voltage sources in series. Or I can just put a square wave, right? If I put in a square wave into the system, into a circuit, a square wave is it's a periodic waveform, and since it's periodic, I can use Fourier series to chop it up into sinusoids, right? So it's like having many sinusoids at different frequencies being put into this circuit, right? I'm gonna look at the corresponding output. It will have a certain shape. This certain shape, I can now change the frequency of my input and see what's going to happen to my output, right? So the frequency content here in a square wave is very massive, right? Square waves have these sudden changes, meaning lots of different frequency content. So the output will sort of give you the frequency response of that system. Sometimes we look at the frequency response by providing a step function to the system. When you take controls, I'm sure you can take controls in chemical engineering. So when you take the controls course, Dr. Nunu, for example, will tell you what is the frequency response. Why? You already took control? You don't want to take classes with Dr. Nunu? I will not record this now. So anyway, so as I said, sometimes we will use square waves or step responses as a way to extract the frequency response of the system, because these square waves or step responses have these sudden changes, like the impulse function. The impulse function has all the frequency components, right? The impulse function contains all the frequency content, right? So we will use this sometimes to extract the frequency response of the system. why do we need to do stuff like this, or why do we need to be able to design circuits with specific frequency responses? For example, we gave the example of a car. I want to design a Lamborghini. So I know the frequency response that you desire. I will take that response and go back and be able to design or select the engine, number of valves, speed of the valves, etc., etc. Same thing with electrical circuits. For example, you want to listen to radio. You know, when you're playing with your radio in your car, you play and click the tuner, right? This tuner is what? Certain frequency that you're listening to, right? This certain frequency is not what's being sent only. What is being sent is, sometimes you will have AM and FM on your radio, right? One of them is called amplitude modulation, and the other is called frequency modulation, right? So what you're actually getting is something like with frequency modulation, you're getting a signal originally that looks maybe certain frequency, and then maybe higher frequency, and then back to the same frequency, higher frequency, lower frequency, etc., etc. Right? So you may be getting this, right? The data is contained in a certain frequency range, right? So your data, the 103.4 or 99.7 or whatever you're listening to, right, will be at a certain frequency range. So how would you extract it? This is an electrical signal, voltage, right? How would you extract that from your system? The antenna is receiving this signal, and then you need to listen only to the data at 103.4, right? So you will take this signal and pass it through an electrical circuit. A box here, this is this signal. This circuit, this voltage here is this signal that you have here. You pass it through a box, and this box will give you 103.4 or 100.3, whatever frequency that you want to listen to, right? How does it do that? It will have to have a frequency response that will eliminate everything but this frequency, right? So in that case, it's called a notch filter, for example. It would, for example, do something like this. Anything at low frequency, anything below 100.3, it will not pass. The magnitude will be 0. This will be magnitude of the output. The output magnitude. This is the output is 0. Okay? The magnitude of the output will be 0. Right? And then this is the 100.3 that you want to listen to. What will happen here? At here, what will happen, you want the circuit to allow everything to pass. So this is, let's say, 1 per unit. Let's say 1 per unit, right? So whatever comes in will come out, right? Whatever comes in will come out, meaning I will take it and multiply it by 1, right? So only at this frequency will this happen. Everything else will be 0, right? So that's what your radio circuits are doing for FM signals. AM signals, it's more like, let's see, modulating by sine wave. This is an amplitude modulated signal, AM signal. Your AM radio works this way. Your AM radio takes data. The data is at this high frequency. Oh, sorry, the data is at the low frequency. Sorry, the AM signal data is at the low frequency, right? And the carrier or the transmission system is transmitting at this higher frequency. This is called the carrier in this case. Right? So the carrier signal is this high frequency, and your data signal is this overriding signal that you have on there, right? So here I have some low frequency overriding signal, and I have a very high frequency carrier. So what do I do to extract my data in this case? And this data, this is a voltage, right? I can make this voltage correspond to a certain sound in a microphone, right? And if I change the magnitude of the voltage, then the sound of the microphone will be different. If I change the frequency, the sound of the microphone will be different, right? So assuming that you know how to create the data, we're not going to create the data right now. Assuming we know how to create the data, and I think we discuss this later on in digital to analog conversion. I'm not sure if we discussed it or not, but it's a simple process. But the idea is, okay, we have data that is this signal that is this low frequency content. So this is a signal that has obviously a high frequency content in this blue waveform, and then this dotted sort of envelope of the waveform is a low frequency, right? So I would like to extract the low frequency content, right? So what do I do? How would I draw this? This is sort of drawing the transfer function. This is frequency, right? At every frequency, here what did I do? At every frequency, I plotted the magnitude of the output, right? And I want to do the same thing here. How would I want this to do? So this is frequency, and this is magnitude of the output. How would this look? At low frequency, I want to get whatever's coming in to get it to bring it out. So I will have 1, let's say multiplied by 1. So 1 at low frequency. And then at high frequency, I want everything to be 0. Right? So I will have to figure out a way to design a circuit to do this. So this is called a low-pass filter response, which means I will have to correspondingly find the design, how to design a low-pass circuit that gives such a frequency response. Here, same thing. This is called a notch filter. We will not study notch filters. We will study high-pass filters and low-pass filters as part of this course, right? But same thing with a notch filter. Notch filter is basically, actually, this is a nice trick. So if you put this, we agree this is a low-pass filter, right? This would be a low-pass filter response, magnitude versus frequency. And then what if I cascade that or follow that with a high-frequency filter? Right? So if I have a low frequency filter and then a high frequency filter cascaded with each other, so I have a signal that's coming in here, and then I put it into another box. One is a low pass filter, and one is then a high pass filter. So I put a low pass filter. I've eliminated all this high frequency stuff. Not there anymore. So everything under the blue is there. And then I pass the same signal through a high pass filter. I eliminated everything here. What am I going to be left with? Everything in this range of frequency, right? So that's why we don't study notch filters specifically, but it's basically a cascading effect of low pass and high pass. So everybody's okay with this idea of low pass filtering, high pass filtering. So now we have to figure out circuits to do this, to fit this criteria, right? And this criteria is what's called the transfer function of the system, right? So the idea, okay, we want a system to behave in a certain way. This certain way or certain behavior is called the transfer function of the system. So this certain input to output performance of a system at various frequencies is called the transfer function. Okay? And we cannot have a circuit that is pure resistors and talk about transfer function, can we? Resistors don't have any time dependence. The voltage and current signals across and through resistors have no relationship with time. You put V, you'll get I, exactly the same shape, scaled by a certain value of the resistor. But you put L's and C's in the circuit, and then things change with time, right? So these circuits obviously will not be pure resistive circuits, and they will not be DC circuits. They will probably be AC circuits, circuits with AC sources supplying them, and then they will probably be circuits with L's and C's, and sometimes R's, or sometimes all of them together, or sometimes just two of them together. So we will have to look at what these things look like. So let's talk more about transfer functions. So as I said, the transfer function is the relationship between the output to the input. So I have a circuit, I will have a certain voltage at the input, certain voltage at the output. I would like to calculate the transfer function. When I say transfer function, it is the ratio of the output to the input voltage. Any questions? Sally, questions? Ask. Yes. Sure. But it has a certain frequency. This is a voltage source with V max, sine omega t, for example. To a resistor here. Of course. Yeah. No, but what will the current look like? I will be what? I max sine omega t, right? So remember, transfer function is the relationship between input to output, voltage or current signal. Right? So here, if I'm looking at V input, what is my V output? V output is the voltage across the resistor. In this case, voltage across the resistor is what? Is the current through the resistor multiplied by the value of resistance, which will be equal to V max sine omega t, because then the voltage here across the source voltage will all be across the resistor in this case. So the output voltage and the input voltage are exactly the same. So my transfer function, if you want to call it a transfer function in this case, is equal to V output over V input. In this case, it's equal to 1. Right? Whatever you put in this case will be whatever you put out. Right? So it's not, there's no frequency dependence of the output. So yes, it's a transfer function. Anything, a ratio between any quantity at the input and any other quantity in the circuit, not the output, I mean any quantity, any two quantities in the circuit. You can find the transfer function between any two quantities, voltage and current, switch opening time, and current. You can find the transfer function between any two physical quantities that you have in the system. Flow rate and pressure, whatever you want. Two things that are in the same system will be related somehow, right? In a car, it's easier to imagine, right? Acceleration pedal, how fast I put the acceleration pedal, or acceleration pedal position, and car speed, for example, right? So you can find transfer function between, but there's also a transfer function within this transfer function of the car, right? So, for example, let's say you want to go at a certain speed, right? Your cruise control system has a transfer function. Sometimes you're going up the hill, and your cruise control will go completely berserk, right? It will do some crazy stuff, right? It will, you will be scared, right? You will like, okay, turn it off, right? Because it's not the transfer function for the controller that is changing your cruise control system is poorly tuned in that case. Why? Because it saw a sudden change, and fine. When it saw this sudden change, it assumed it had to make sure that it accelerates very quickly so that it can try to bring the car back to speed. But when it does that, the car actually goes very fast, and you hear, or maybe it doesn't go very fast, but you hear the engine roaring sometimes, right? And it's not necessary. An application like that, so what? If that's what happens, you can go slowly to your set point, right? Versus you do this without a cruise control system, the transfer function is the human, right? It's you're going to look at the accelerator or the acceleration, the speed dial reading, and you will change your position. So you are a transfer function within that's affecting the output of the car. So there's a transfer function between the dial position and your brain processing it and you pushing the pedal. This is a small system within the bigger system, which is the car, right? So the physical systems will have multiple transfer functions cascaded, and you will take that with Dr. Nuno as well, even though Sally laughs when I say Dr. Nuno. So Dr. Nuno will give you systems with cascaded transfer functions. Some transfer functions will be in series, like this car and me in there, right? some things will be in parallel. I cannot come up with a good example of something like that in parallel, but something may be happening when in parallel with you looking at the car, for example. Some safety system is making sure that you don't accelerate beyond a certain value. Something like that is happening in parallel to you, and both of these parallel systems will affect the next thing that's happening as well, right? So Dr. Nuno will give you blocks, you know, series, parallel, and things feeding back each other, and then you will simplify all of these. Because at the end of the day, the car will have a transfer function. That includes all of these things together. So you will take some block diagram reduction methods in control that will, okay, this is now the global transfer function for the system. And sometimes you will, okay, I want to open it up here and look at between only these two points. And if the transfer function is poor, for example, like if the response is too slow, if I'm blind, right, and I cannot look at the dial, then I have to go and interfere with another control system that maybe gives me a braille reading of the speed, even though even though I shouldn't be driving if I'm blind. But it's an exaggeration. Anyway, so it's the ratio of the output over the input in this case. So for electrical circuit, it's easy. Okay, it's any two either. We either have voltage or current, right? It's either voltage or current in electrical circuit. And in this case, okay, the output and the input are in phasor form, and since they're in phasor form, then they are complex quantities. So this transfer function will also be a complex quantity. Okay. So, for example, in the car example as well, complex quantity means it has a magnitude and an angle, right? So in the car example, two cars with different transfer functions. Let's say if the magnitude was the same, but the angle was different, and two people push the pedal on the car exactly the same speed. What will happen in this case? The cars will do what? The cars will definitely go to the same speed because the magnitude of the transfer function is the same. But because of the phase angle, one will be delayed with respect to the other. Right? That's physically what an interpretation of that. So I'm just saying this is a complex quantity. Transfer functions are complex quantities. They will have magnitude and they will have angles. So this is an example where you have a signal here that has, that looks like this. This signal, it's a periodic signal. So since it's a periodic signal, I can take it and chop it up using Fourier series. It happened to be a summation of these two signals, for example. Then I pushed it. So here I have an h of f. I have a transfer function here at this line here. So these two signals are now, they're actually one signal, but you can mathematically reduce two specific signals. You're going to push this through a block. This block will have an effect on magnitude and phase, depending on frequency. Right? It will have an effect on magnitude and phase depending on frequency. That's transfer function. Right? So this happened to do what? This signal happened to be translated to this signal. This signal happened to be translated to this signal. So what is this block doing? This is obviously this is a low frequency signal. What happened to the low frequency signal? Its magnitude sort of was amplified. How about the high frequency signal? The high frequency signal, two things happened to it. The magnitude changed. The magnitude was damped significantly. But what happened to its phase? Look at the peak. This line here is at the peak of this signal. How about this line here? Is it at the peak of the signal? No, it's actually advanced a little bit. Right? So the phase of this high frequency signal actually advanced a little bit versus the input. And the magnitude was suppressed. And here, for the low frequency content, the magnitude was amplified, then phase did not change. Right? So I can sort of draw something. So this is magnitude of the transfer function, magnitude of h, with frequency. and then this is phase angle of h with frequency, right? So I can sort of draw something crooky now, approximate, and say, okay, at the low frequency, so let's say this is my low frequency side is here, and on the low frequency end, my input signal was multiplied by a gain of, let's say, 2, for example, right? And then at the high frequency end, the signal was multiplied by a gain of, let's say, 0.4, point whatever, 0.1 or something, right? So here, right? Approximately, I don't know the number exactly, right? And between them, it's doing something. It's going to go from here to here, right? It can go between them this way, right? Or it can go between them this way. It can go between them this way, many ways. Do we agree? And the way it goes between them will depend on how I design the circuit inside this box, right? So, but it will, the asymptotes, which we will typically use, asymptotes are what you want as an engineer. I want back of the envelope type calculation. The asymptotes at low frequency will be like this. Asymptote at high frequency will be this way, right? So this is what happened on the magnitude plot. How about the phase plot? In the low frequency, the phase changed by 0. There was no change in phase. How about in the high frequency side? There was a positive change in angle of, I don't know, 5 degrees, for example, whatever, right? 5 degrees, right? So the angle looks like this in that case. Okay? So this is magnitude plots and phase plots. We will do a lot of those in this chapter. Okay? But basically, these are what's inside. These are the frequency response of this circuit, meaning the relationship between voltage at the input or signal at the input and signal at the output of this box at every frequency. That's what these are. That's fine. Yeah, 5 degrees. I said 5 degrees. I'm standing upside down. I mean, 5, yeah, you can do that. I just drew 5 here. Sure, you can say this is minus 5. If I say this is minus 5 and this is 5, then I will draw it this way. It's fine. I understand your point, and we will, of course, have to agree on a way to draw this stuff. Yes, and I agree that typically 0 actually will be down here too. Why you should have told me, why did you bring 0 up there? That's a better question. But we will agree on a way to draw it. I just drew something just to illustrate the process. But next class we will agree on how to draw them, and there will be a certain process of how to calculate the transfer function. But this is sort of the basics behind transfer function, and this is called body plots. These are called body plots. Right? So we will figure out how to do this stuff next class. If you haven't taken your exam, you can